In this video, we are going to talk about two of the colligative properties called boiling point elevation and freezing point depression. So colligative properties, so let's spell this out, colligative properties are basically properties that depend upon the number of particles present. So we'll say the number of particles present, and not necessarily the type of particles. So colligative properties are basically based upon the numbers of particles present in a solution, not necessarily the type of particles. So for example, if I'm making a solution, colligative properties for the boiling point elevation, it really doesn't matter if what type of salt that I use. All that matters is the number of particles that the salt makes in the solution, and you'll kind of see how this works out as the video goes on. But anyhow, these boiling point elevation and freezing point depression are two aspects of a broader category called colligative properties. So let's go ahead and throw out some mathematical formulas. Let's do boiling point elevation first. So if I elevate something, it means that I increase it. So boiling point elevation is exactly what it sounds like. Whenever you add a solute to a solution, you are going to increase the boiling point of that solution. So the temp or the formula that we're going to look at here looks like this. So it's T, we'll say, or let me get a little more room here. So we're going to say delta T B, and I'll go through and explain what these mean in just a second. Let's just get the formula down first. K B times M times I. So this is a lowercase cursive I. So the delta TB delta, this triangle looking thing, is a Greek letter. The Greek letter is delta. So delta means change in. Change in. So it's a change in something. So for example, if I have $100 in my pocket and I go into the store and I buy some clothes, some shoes, maybe some folders for school, and I come out with $70. So I went in, I started out with $100, and so this is what I went in with, and I come out with $70. So I come out with $70. So if I started with 100 and now I have 70, how much money did I lose? Well, that's just simply 100 minus 70. I spent $30. So in this particular example, this would be my delta money. So delta money. This is my change in money. I had 100, now I have 70, and 30 is what I spent. So that's the change in the amount of money that I had. So T stands for temperature. In these particular types of problems, temperature is going to be in degrees Celsius, and the B just stands for boiling. And as you'll see later, the formula for the freezing point depression looks a lot like the formula for the boiling point elevation. So we keep going. KB. K normally stands for a constant, and in this particular example, K does stand for a constant. Um, the constants are given in a chart. Usually, if you have a test, these constants will be given to you. I know especially in my class, I don't require the students to memorize constants. I will often give them to them on a test or quiz. But anyhow, the K just stands for the boiling point elevation constant for whatever solvent you're using. And this will make more sense once we get down to the problem. M stands for molality, so it's a little m, so it's molality, not molarity, but molality. Okay, and the I stands for something called the Van't Hoff factor. So Van't Hoff factor. So if I remember correctly, it was named after, I guess, some scientist. Maybe this was his whole name. But anyhow, it's named after somebody. So Van't Hoff factor. And the Van't Hoff factor basically deals with ionic compounds. And because ionic compounds ionize, or they dissociate when you put them in solution to make ions. So for example, if I had normal salt, NaCl, table salt. So what's going to happen when I put this into water, basically I'm going to make sodium ions and I'm going to make chlorine ions. So I'm going to make 1 and 1. So the Van't Hoff factor for sodium chloride would actually be 2, because I make 1 ion of sodium and 1 ion of chlorine, so that gives me 2. But now if I had something like, let's say calcium chloride, where it's CaCl2, if I were to put calcium chloride, let's make that look like a Cl, so Cl2. So if I had calcium chloride and I put it in solution, I'm going to have Ca plus 2 ion, and I'm going to have Cl minus 1, and I'm also going to have another Cl minus 1. So I've got 1, 2, 3 different ions in solution. So the Van't Hoff factor for something like calcium chloride is 3, whereas the Van't Hoff factor for sodium chloride was just 2. Now, you really only have to worry about the Van't Hoff factor if you have a covalent, or not covalent, sorry, if you have an ionic compound, because ionic compounds are the ones that actually split up into ions. And one way you can tell something is ionic is it's got a metal in it. In this particular example, sodium and sodium chloride, sodium is the metal, and in calcium chloride, calcium is the metal. Okay. If you ever do have a covalent compound, so let me do a different color here. Let's choose say green, and I'll go up here. So an example of a covalent compound would be glucose. Glucose is C6H12O6, and this would be covalent. And we know that this one is covalent because carbon is a nonmetal, hydrogen is a nonmetal, and oxygen is a nonmetal. So all these are nonmetals, so that means a covalent bond, so no ions form. So if no ions form in solution, basically the number that's going to be associated with covalent is 1. So you would put 1 in for your I, or you could just leave it out, because once we take our Kb times our molality, if I is actually 1, and it's going to be the same thing. So Kb times m is the same thing as Kb times m times 1. So if it makes you feel better, you can put a 1 in for the I if you have a covalent compound, or you can just leave it out. Mathematically, you'll get the same number. So really quickly before we move on to the problem, the formula for freezing point depression looks like this. It looks an awful lot like the first one we just wrote down. So it's delta Tf is equal to Kf times molality times a lowercase cursive I. So if you'll notice, the only thing that changes is the little subscripts here. Right? They go from a B, which stands for boiling, to F, which stands for freezing. Okay, so mathematically, these will work out the same. Okay, so let's go ahead and let's do another problem. Actually, I think we may be running out of time for this video. So I'm going to go ahead and stop the video here, and then we'll pick up in the next video using the information that we've just talked about in a particular problem.